Now let's connect the heat, like heat transfer, to what's happening within the substances or the chemicals. Molecules and atoms have energy stored within them. It has to do with their motion on an atomic or molecular level, the bending of bonds, attractions, and so forth. All of those create potential energy of different types on the microscopic level. And this overall internal energy we use U for. And U is the energy of the molecules and atoms. Again, it's a potential energy overall. When you're doing chemical reactions, this is the kind of energy that can be released and used to do work. It's the kind of energy that is released like when you're burning a fuel. In chemical reactions, we don't usually focus on what we call bulk energies, and those would be like to do with gravity or to do with something flying across the room or something like that. We usually focus on what's happening with the chemicals themselves. So like in lab, when you're doing an experiment, you have a reaction going, if it falls on the floor in the middle of the reaction, you're not going to consider that energy difference that's caused by gravity and the potential energy associated with height. We ignore those things. We're interested in what's happening with the molecules. Okay, so as far as the molecules go, the overall stored energy is dependent on the energy of the particles and molecules themselves, but also there's a term that has to do with pressure and volume. And so enthalpy is the term for the potential energy, the stored heat of the substances. And so that's usually what we will be talking about in here, is the enthalpy. And again, think of it as the internal energy of the substances. This pressure volume term, we're going to kind of make an assumption that that is not changing in our chemical reactions. Otherwise, like for example, if a reaction produced a gas and that gas expanded, we would have to take into account a change in pressure and volume. We're going to make the assumption that that's not changing. So we will be interested in delta H, delta being the change in internal energy of the substances during a chemical reaction, and we'll assume that that's the same as the change in the internal energy if pressure and volume remain constant. Anyway, so this is the main thing we'll use, delta H reaction. It is, again, the change in internal energy of the substances during a chemical reaction. And so if the substances are losing energy, like for example, if you have gasoline, which has a lot of enthalpy stored in it, and you're burning it, then the products of that reaction, the CO2 and water, they have less energy stored within them, and the difference is released as heat. So if delta H is negative, that means the substances lose energy. Then heat is released, and the reaction is exothermic. If the substances are absorbing energy, then the reaction is endothermic. So again, get it in your head that when we say enthalpy, we're talking about the substances and how much is stored in them as chemical potential energy. I like to look at it graphically. It helps me get it. So hydrogen, enthalpy here, remember we're thinking of that energy of substances. We've got an extra bump there. That's what this means. So if the reactants, this would be like gasoline, they have a lot of enthalpy stored in them. If the products have less enthalpy stored in them, then you're going to have energy released, and this is exothermic. And then the opposite is true. If the reactants don't have very much energy, like this would be something like plants do. They take CO2 and water that don't have very much energy. They absorb energy from the sun, and they make products like sugars that have more energy stored in them. This is endothermic. So we can use a calorimeter to measure that amount of heat that is absorbed or released. And let me fix my calorimeter here. It looks like it shifted a little. We need water surrounding that reaction. So a calorimeter allows us to measure how much heat is absorbed or released by a reaction. This reaction looks like it's exothermic. It's giving heat, so I would expect this water to warm up. So just like with the metal, the hot metal put in the calorimeter and the water warming, we can see the temperature change of the water and then see how much heat this reaction gave off. And that's what this is down here. This would be where we use like a Q-SMAT equation for the water, and we can see how much heat the water absorbed in this case, and then figure out the heat of the reaction, what's happening with the substances. Anyway, another constant or another way of doing this is to use this C-cal, that's the calorimeter constant. And it takes into account warming and cooling of the whole calorimeter, not just the water. So we could do just the water, but it's better if you have a calorimeter constant that takes into the account of things like if you have a stirrer in here, or a thermometer sticking in there, and also the inside surface of this. It takes into account all of the heating and or cooling of that. So another word for this calorimeter constant is that it's the calorimeter's heat capacity. And so in a way, you can think of this C-cal, it kind of takes the place of the specific heat and mass. Okay, and then so this little part down here is like we did with the metal. Whatever we calculate for the Q for the calorimeter, we'll change the sign, and that will tell us the heat of the reaction, the delta H reaction.